G'day viewers, it's been a while since I've done a personalised video, but I felt it was time to do one again, particularly on such an important topic as the integration of general relativity with the quantum vacuum. Firstly, I just want to apologise if I'm a little bit different. I've got a tooth issue, and my jaw is a little bit swollen over here. I'll be getting that fixed tomorrow, I hope. So just wanted to apologise for that up front. In this episode, I'm going to walk you through two methods which demonstrate that the EGM construct successfully integrates general relativity with the quantum vacuum. Method 1 simply multiplies the Ricci scalar by a quantized version of the number 1 at a point in space, which we call the unit harmonic operator. This unit harmonic operator is bounded by physical quantum vacuum cutoffs. We call the upper boundary the quantum vacuum spectral limit. This totally eliminates one of the key issues preventing the integration of general relativity with the quantum vacuum, termed ultraviolet divergences. So basically, the infinite energy in a vanishing volume problem, which is a key upset within quantum electrodynamics, simply doesn't exist under the EGM construct. Method 2, simply speaking, takes the unit harmonic operator and averages it over a region of space-time. So method 2 reduces to method 1 in the pointwise limit. In fact, any and all solutions claiming to integrate GR with the quantum vacuum must converge to our method 1 solution in the pointwise limit. This means that method 1 actually denotes a litmus test for any mathematical model going forward. This applies to loop quantum gravity, string theory, or anything else. Method 1 is a top-down approach. It's a fine-grained engineer's solution. Method 2 is a bottom-up approach starting from the Einstein-Hilbert action, which yields a coarse-grained solution. Both methods work because of the quantum vacuum spectral limit. The number of harmonic modes for all non-Planckian systems is so large, and the corresponding spectral frequency cutoff is so high that the quantum mechanical nature of gravity cannot be directly observed with current technology, and therefore gravity appears to be the smooth phenomenon described by general relativity. Okay, let's get into it. This slide shows three equations. At the top, we see the classical Einstein equations, that is, standard general relativity. Below that, we see method 1, the fine-grained solution. We also refer to this as being an engineered solution. It's a top-down approach. The only modification is the insertion of the unit harmonic operator, which acts on the Ricci scalar term. Below that, we see method 2, the coarse-grained solution. We refer to this as being a variational solution. It's a bottom-up approach because it commences from the Einstein-Hilbert action. One could almost say that it's an organic solution. Here, the unit harmonic operator acts on the effective Einstein tensor, not just the Ricci scalar. Notably, both modified equations reduce to the classical limit when the unit harmonic operator equals 1, which holds for all observable systems. Moreover, it is also important to understand that method 2 reduces to method 1 in the pointwise limit. That is, when the number of quantum vacuum harmonic modes tends to infinity or a volumetric element tends to 0. Okay, now let's walk through method 1 and 2 in a bit more detail. Let's begin with the top half, method 1, the fine-grained solution. Method 1 is an engineered solution. The modified Einstein equations shown here have the unit harmonic operator inserted directly into the field equations, multiplying the Ricci scalar term. This operator encodes the discrete harmonic structure of the quantum vacuum. The unit harmonic operator is a Fourier series of odd harmonics representing the number 1 as a sum of waves. The sum runs over a double-sided spectrum from negative n to positive n in steps of 2. Where does n come from? Well, it's the quantum vacuum spectral limit appearing as n sub omega beta, which depends upon position and mass. Now, a key point about the harmonic distribution. The method 1 harmonic distribution obeys a Fourier series. Because the spectrum is a double-sided Fourier series, the total number of harmonic modes is n plus 1. When n tends to infinity, the unit harmonic operator becomes exactly 1 and we recover standard general relativity. For any real system, n is enormous, so the unit harmonic operator is observationally indistinguishable from unity. However, the harmonic structure remains, and we later use it to quantize gravitational acceleration point by point. Now look at the bottom half, method 2, the coarse-grained solution. Here, the modified Einstein equations are written differently. The same unit harmonic operator now multiplies the effective Einstein tensor. The background metric and stress energy tensor appear unchanged. So then, how does the vacuum enter? Well, it enters through an effective metric shown on the left. Phi is a dimensionless scalar condensate, that is, a finite sum of orthonormal mode functions averaged over n modes. Once again, n is set by the quantum vacuum spectral limit. Notice the difference. The method 2 harmonic distribution obeys an integer sequence from 1 to n, not a Fourier series. Consequently, the total number of harmonic modes in method 2 is simply n. The macroscopic unit harmonic operator is defined as the spatial average of the inverse of the scalar condensate across a space-like hypersurface. The spatial form of the unit harmonic operator appears at the bottom of the slide. This coarse graining gives us a smooth, time-dependent operator which replaces the local fluctuations of the scalar condensate. So then, what is the relationship between method 1 and method 2? As a volumetric element tends to zero, or as the number of harmonic modes tends to infinity, method 2 converges to method 1. In fact, this means that all potential methods, by others, must always converge to the method 1 solution in the pointwise limit. That is, any physically correct theory of gravity must, at a point, reproduce the same numerical predictions as method 1, that is, the predictions of classical GR. Thus, whilst the two methods differ in their harmonic distributions and mode counting, they lead to identical empirical outcomes. This convergence is powerful evidence that the framework is robust. What can we say in closing about these methods? Method 1 quantizes the vacuum at a point. Method 2 averages it over space. However, in the limit of a point, or infinite modes, they become indistinguishable. Think of it like this. Method 1 is a pixel, and method 2 is the picture, but they're part of the same image. Okay, let's now take a closer look at the unit harmonic operator. Let me start by noting that you can pause the video at any time and read the text appearing on screen. Okay, let's dive into the detail. The unit harmonic operator is always the number 1, written as a sum of odd harmonic waves, specifically utilising a fully rectified square wave to do it. However, there are two ways to use the same unit harmonic operator. We can apply it to a point in space, or we can apply it over a volume of space. If we apply it to a point in space, we utilise the temporal form. If we apply it over a volume of space, we utilise the spatial form. So then, the obvious question becomes, why do we need to apply it differently over volumetric spaces? Well, because the quantum vacuum spectral limit is coordinate specific and possesses a different value at each point in space, we need a tool to compensate for this attribute over a spatial volume. That's why method 1 is different from method 2. In method 1, the unit harmonic operator relates to a single point. It's inserted directly into Einstein's equations, then later used to break gravity into tiny steps. That is, gravitational acceleration is quantized. In method 2, the unit harmonic operator is spread over a volume. We first define a scalar condensate, which represents local vacuum activity, then average its inverse over space and time. That average is equivalent to the same unit harmonic operator, but now it is a volume-averaged smooth version of unit harmonic operator. So then, what are the key differences between methods? Well, in method 1, the unit harmonic operator is applied point by point. However, in method 2, the unit harmonic operator is spread out over a volume. Therefore, the unit harmonic operator itself never changes, only how we use it. This slide explains why we need both fine-grained and coarse-grained versions of the unit harmonic operator. The framework uses the fine-grained level, method 1, to extract quantum vacuum structure from first principles, that is, harmonic cutoffs, equilibrium radii, photon mass, and so on. It then applies coarse graining, method 2, to show that for everyday and cosmological scales, quantum effects average away, leaving classical general relativity intact. No other quantum gravity proposal has such a clear coarse graining prescription that recovers GR exactly without free parameters. Now, let's discuss the 5 key points. First, both methods define the unit harmonic operator as the Fourier series of a fully rectified square wave converging to unity. Method 1 writes it explicitly. Method 2 refers to it by description. No algebraic conflict exists. Second, in both methods, the operator multiplies curvature terms, that is, either the Ricci scalar or the Einstein tensor, to introduce a discrete harmonic structure derived from the quantum vacuum. When the number of modes is much greater than 1, which is true for all non-Planckian systems, the unit harmonic operator tends to unity and classical GR is recovered. Third, method 2 spatially averages the inverse of the local scalar field, whereas method 1 works directly with the Fourier form. Averaging is a bridge, not a change. That is, the unit harmonic operator still converges to unity as the number of modes increases. Fourth, in both methods, because the unit harmonic operator is effectively unity for all observable systems, the modified equations reduce to the standard Einstein equations. No inconsistency with energy momentum conservation arises. Method 2 explicitly discusses conservation laws and shows that they are preserved to extraordinary precision. Fifth, method 1 focuses on the algebraic insertion of the unit harmonic operator into the field equations and its verification via the a priori Hubble constant prediction, that is, 2008 versus 2013. Method 2 elaborates the connection to the scalar condensate and provides a more detailed justification of why the operator is effectively exact. They are two presentations of the same underlying idea, with method 2 offering additional granularity. Okay, let's summarise the unit harmonic operator. The unit harmonic operator has a single definition, that is, a Fourier series converging to unity. Both methods use it consistently, just with different levels of averaging. The truncated harmonic series yields a value indistinguishable from unity at all observable scales, which is identical in both methods. Let's take a closer look at method 2, that is, the ground-up approach. First, we apply the action principle to the polarizable quantum vacuum. We know that the quantum vacuum must always settle into its lowest energy state due to the principle of least action. In flat spacetime, this is termed the zero-point field. Any higher state would require extra energy which the quantum vacuum doesn't have. So, the quantum vacuum naturally organises itself into a discrete harmonic spectrum. The only kind of spectrum it can organise itself into has a Fourier distribution. Any other form of mathematically quantized sinusoidal composition would represent an elevated energy state. That is, it would not represent the ground state of the quantum vacuum and therefore would not satisfy the action principle. This minimization of action enforces an equilibrium condition. This means that if we were to introduce any matter into this zero-point field, the quantum vacuum reacts by becoming polarized. Within this framework, polarization means that matter displaces spacetime, and that displacement induces a gradient in the spectral energy density of the zero-point field. This gradient is the origin of gravity. Without a gradient in the spectral energy density of the zero-point field, gravity does not exist. This applies to any and all situations where matter is involved, regardless of scale. With matter introduced into the zero-point field, the quantum vacuum is now in an elevated energy state. It is transformed into the polarizable vacuum. Yet even so, the quantum vacuum remains in equilibrium and in its lowest energy state with respect to the new boundary conditions. So, what else does this mean? Well, since the least action principle requires an equilibrium condition, then by necessity, the mass energy density of the matter present must equal the spectral energy density of the quantum vacuum. Therefore, mass energy density equilibrium with the quantum vacuum is a fundamental law of nature. This leads to the concept of a scalar condensate, and from there, the unit harmonic operator as its spatial average. The scalar condensate is non-dynamical, dimensionless, and algebraically constrained. Its job is to bridge the discrete quantum vacuum with continuous classical geometry. That is, it regularizes ultraviolet divergences, modulates the metric with quantum corrections, and guarantees that classical GR is exactly recovered at all observable scales. From the scalar condensate, we land at the effective metric. The effective metric is the central geometric object. It integrates quantum vacuum fluctuations into general relativity whilst leaving all classical predictions intact. The effective metric is then embedded within the effective Einstein tensor. The effective Einstein tensor is the curvature term in the modified equations. It encodes quantum vacuum effects via the scalar condensate and reduces to the classical Einstein tensor when those effects are negligible. In other words, it bridges the quantized vacuum structure with classical gravitational dynamics. So then, what's the difference between the effective metric and the effective Einstein tensor? Well, the effective metric defines the geometry, whilst the effective Einstein tensor denotes a specific curvature construct derived from that geometry. Okay, let's now summarise what we have learned. Starting with method 1, we've seen how the unit harmonic operator is an exact Fourier series using only odd harmonics. It oscillates around the value 1 with a tiny amplitude, that is, about 1 over n. We use this level for quantum scales, thereby deriving the quantum vacuum spectral limit, particle radii and discrete acceleration quanta. Turning our attention to method 2, we've seen how the unit harmonic operator can be applied across a volume to generate the spatial average of the inverse of the scalar field. The resultant spatial form of unit harmonic operator is smooth, effectively constant, and unity for all macroscopic systems. The spatial form of the unit harmonic operator applies to astrophysics and cosmology. Both methods start from the same Fourier square wave definition of unity. Both recover classical general relativity whenever the number of harmonics is much greater than 1, which is true for all non-Planckian systems. And they are fully consistent. They simply describe the microscopic and macroscopic levels of this same unified model. In conclusion, the unit harmonic operator bridges the quantum vacuum and general relativity, fine-grained for particles, coarse-grained for the cosmos, without changing any observable prediction of Einstein's theory.